Good day, everybody. Today we are going to talk about chapter 12. So we are going to conduct a goodness of fit test for a multinomial experiment. This test determines whether two or more population proportions differ from each other or any predetermined set of values. For example, are four candidates in an election equally favored by voters? Or do the market shares differ between the four firms in a heavily concentrated industry? So these are examples of the use of this goodness of fit test, as you will see. So multinomial experiment consists of a series of n independent trials such that there are k possible outcomes called categories. The probability p associated with ith term remains the same, and the sum of the probabilities is 1. That is p1 through p1 plus p2 plus p3 plus dash 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 up to pk is 1. Okay, so these k outcomes are called categories, as you will see, and the sum of the probabilities of each outcome is equal to 1. The hypothesis test, the null hypothesis, the population proportions are equal to one another or they equal to a specific value. Equal population proportions. If there is equal population proportions, then H0 is P1 equal to P2 equal to P3 equal to P4 equal to 0.25. That's your null hypothesis. That's your status quo. And your alternate hypothesis is not all proportions are equal to 0.25. Unequal population proportions, null hypothesis could be P1 equal to 0.4, P2 equal to 0.3, P3 equal to 0.2, and P4 equal to 0.1. So this is the status quo. This is what the proportions we think will be right, correct. And alternate, not all population proportions are equal their hypothesized values. Restaurant food quality. Last year, the manager at a food restaurant surveyed its patrons to rate the quality of its food. Excellent is 15%, good is 30%, fair is 45%, poor is 10% of the votes received. Based on the responses, the management decided to revamp the menu. Recently, the same question was asked of a random sample of 250 patrons. Okay, 40, and they get the following ratings. 46 people said the food was excellent, 88 said it was good, 105 said fair, and 16 said poor. Determine whether there has been any change in the population proportions calculated 1 year ago. Okay, so restaurant food quality. Let the earlier population proportions be hypothesized proportions for the test and denote P1, P2, P3, and P4 because there are 4 categories. The population proportions of those that responded excellent, good, fair, or poor. That is P1, 1 stands for excellent, 2 stands for good, 3 stands for fair, and 4 stands for poor. So state the hypothesis. So null hypothesis H sub 0, the proportions are same as last year. P1 is 0.15, P2 is 0.3, P3 is 0.45, and P4 0.1. Alternate, not all population proportions equal their hypothesized value. Okay. Restaurant food expected frequency. Compute an expected frequency for each category. Multiply the same size sample size n by respective hypothesized population p. For example, if the survey is consistent with last year's result, we expect the expected value for excellent category is n times p1, which is 250 times 0.15 is 37.5. This is the expected value based on null hypothesis. Test statistic compares the expected frequencies to the frequencies we actually observed. Okay. So we are comparing the expected frequency with the actual observed. For a multinomial experiment with k categories, the value of the test statistic is chi-square degrees of freedom is equal to df stands for degrees of freedom, summation, that's a summation sign, sigma. So for each category, we subtract the observed minus the expected, square it up, divide by the expected value. And degrees of freedom is k minus 1. And the expected is n times pi, are the observed and the expected frequencies in the category. Okay, OI and EI. OI is the observed category, EI is equal to n times P. I is the expected expected count for the ith category. The chi-square degrees of freedom test statistic follows a chi-square distribution. Now, degrees of freedom is k minus 1. What is k? Number of categories. For the food problem, the 4 categories, degrees of freedom will be 4 minus 1, 3. Okay. The test is valid when the expected frequencies for each category are 5 or more. Okay. So how to do this in the calculator? So the expected, first column is the 4 categories: excellent, good, fair, poor. Second column is the hypothesized proportion, which is same as last year. Okay. And then we did the expected frequency count in each category. So for example, total number of customers was 250 times 0.15. Expected category for excellent would be 37.5. Expected count or expected frequency for the good category will be 250 times 0.375. Okay. Now, similarly for fair, it will be 250 times 0.45. This is the expected value, 112.5. And poor is 250 times 0.1 is 25. Remember the observed values. The observed values are, if you remember, the observed values are 46, 83, 105, and 16. So for example, for excellent, the observed value is 46. So that is the OI for excellent. OI for good is 83. OI for fair is 105. And OI observed value for poor is 16. So let's do it with our calculator. So first thing we will do is second plus button on top of the enter button on the bottom right, then number 4, clear all list, done. Then we will press the stat button, 1. In L1, we are going to put the observed values in 46, then 83, then 105, and then 16 in. Then press the right cursor key on the top right corner to move the cursor to the first line in L2. Okay. And enter the expected counts in L2, which is the first one is 37.5, second one is 75, next one is 112.5, and last one is 25. So observed in L1, expected in L2. Then we will do stat, then test, highlight test on the top row, and scroll down with the down arrow key. Do not use the first chi-square test. Use the chi-square GOF. GOF stands for goodness of fit test. That is the second category of chi-square. Hit enter. Your observed is in L1. Your expected is in L2. Your degrees of freedom, you have to put it in the third line. Remember, there are 4 categories. 4 minus 1 is 3. Okay. And then you go down to calculate and calculate the chi-square statistics. So test statistic chi-square is 6.52. Notice the p-value is 0.088. So what does it mean? This p-value is the probability of getting a test statistic as extreme as 6.52, provided the null hypothesis is true. Now 0.088 is the probability value. Usually we select level of significance alpha equal to 0.05. That is, we take a 5% risk in making a type 1 error, okay? And p-value here is 0.0888, which is greater than 0.05. When p-value is greater than alpha level of significance, which we assume to be 0.05, we do not reject the H0, okay? So p-value is greater than 0.05, so we do not reject H0 in the last bullet and cannot conclude that the proportions differ from 1 year ago. There are 5 companies that manufacture a particular product. A marketing analyst wonders whether the market shares have changed since 2010. The table provides the market shares for 2010 and the number of customers who recently purchased the product at each firm for 200 surveyed customers. Okay. Use alpha equal to 0.05 to determine the market share if the market shares have changed since 2010. So in 2010, the market shares are given and number of recent customers are also given. This is the observed count. So our null hypothesis will be the same proportions as that in 2010. So it will be P1 equal to 0.4, P2 equal to 0.32, P3 is 0.24, P4 is 0.02, and P2 is 0.0, P5 is 0.02. Alternate hypothesis, not all the population proportions are equal. They're hypothesized, means educated guess value, means a null hypothesis. Now, they have surveyed 200 customers. They have given us the observed percent. So we will multiply the observed percent with multiply it times the 200 to get the expected counts, which are shown here. Okay. So here E1 and E3, here E4 and E5, rather E4 and E5 are less than 5. So we combine them to make it 8. Okay. So, and we will also combine 10 plus 6 for number of percent for this is for the observed, since the observed tree counts for farm 4 and 5 are less than 5, we combine them together to make it 8. Okay. Similarly, we'll combine the P4 and P5 expected values also. And also we will do the null hypothesis comparison, combine them together. Okay. So notice the current observed values are 10 plus 10 for category farm 4 and 6 for farm 5. If you combine them together, the observed becomes 10 plus 6 is 16 for category 4 and 5 combined together. Okay, so let's do it by our calculator. So first put the calculator on, second plus 4, clear all this done, then stat 1. In L1, we are going to plug in the observed values. So it will be 70, 60, 54, and last two categories combined is 16. And there are only 4 categories now. Now the expected values are 80, 64, 48, and 8. Remember, the expected are obtained from multiplying the total number of customers with the uh, expected percent in null hypothesis. Okay. So then we press the stat button, highlight test on the top row, scroll down to chi-square GOF, and hit enter. Observed is L1, expected is L2. 1, 2, 3, 4 categories now because we combined actual original 4 and 5 to 1. So degrees of freedom is still 3, and we calculate. Our chi-square is 10.25. P-value is 0.0165, which is less than 0.05. Remember, p-value is the probability of getting a test statistic as extreme as 10.25, provided the null hypothesis is true. And the probability of that happening is 0.0165, which is less than the level of significance of 0.05. Hence, we reject the null hypothesis since p is less than alpha. So at 5% level of significance, we conclude that some markets. So if we reject the null hypothesis, we are rejecting the hypothesized value, which we think the proportion, which we thought the proportions will be in that order. So since p-value is less than 0.05, we reject the null hypothesis. At the 5% significance level, we conclude that some market shares have changed. The goodness of fit test examines a simple qualitative variable. A test of independence, also called a chi-square test or contingency table of a contingency table, is used to analyze the relationship between two qualitative variables. Okay. The competing hypothesis can be expressed as null hypothesis. The two classifications are independent. Alternate, the two classifications are dependent. Okay. Contingency table generally shows frequencies for two qualitative categorical variables x and y, where each cell represents a mutually exclusive combination of the pair of x and y values. X is along the rows, y is along the columns. Okay. Each variable has 2 or more categories. The test for independence is based on the expected and observed frequency for each cell in the table. Let Oj denote the observed frequency in the row I and column J. Let Eij denote the expected frequency in row I of column J. Formula to calculate expected frequencies for each cell in a contingency table is row I total times column J total divided by sample size. And this is the formula. Scary looking formula, but we will use a calculator, so don't worry about it. Degrees of freedom is row minus 1. Number of rows minus 1 times number of columns minus 1. Oj and Eij are the observed and expected values. The test is valid when expected frequencies for each cell are 5 or more. Okay. So, does the brand of compression garment purchase depend on customer's age? So there are 2 categories of age. So 2 rows, okay, and there are 3 columns: Under Armour, Nike, and Adidas. 80 age group and brand names are independent. Alternate age group and brand names are dependent. Okay. So the expected counts are calculated by multiplying the column total times row total for expected value 1, 1, which is column 1 and row 1. It will be row total 396 multiplied by column total 228 divided by the total is 600, a grand total. Okay. So how to do this problem in using calculator? So again, second plus 4 clear all list done. Then we will go to second and x minus 1 in the first column, x to the power of minus 1, second and x to the power of minus 1 button will give you matrix. Then we will press 1. Okay, sorry. Second stat button, x minus 1 matrix, okay. Sorry, the second x minus 1 math button, your cursor is sitting on number row 1 and is on top line names. Move in the top line to edit. And we are going to edit, put the cursor on the top line on edit and number 1. Okay. So we'll press number 1. Okay. What type of a matrix it is? First comes row and then comes column. So we have 2 rows and then enter. And the second number is the number of columns, which is 3 in this case, and hit enter. Okay, so it's a 2 by 3. Notice there are 2 rows open up and 3 columns. So in the first row, we will place first number 174. Then hit enter. Next number in the first row is 132 and enter. And then 90 and enter. Second row, first column, 54 and enter. 72 and enter. 78 and enter. Okay. Now again press second button and x minus 1 matrix. Go to edit and this time move the cursor down to number 2, which is matrix B. Okay. And hit enter. Again make it a 2, enter, 3, 2 rows, 3 columns. Okay. Now we are going to do the expected values. So the expected values are given. Okay. So expected value of the first row, first column is 150.48. Next one, expected value, first row, second column, 134.64. Then the last one, expected value, is first row and third column is 110.88. $110.88. Now go to the second row. Expected value first column is 77.52. Then second row, second column is 69.36. And then second row and third column 57.12. So you enter those values for matrix B. Now we have to do the test. Okay. So stat button, test, and scroll down. Now you will scroll down to the first chi-square test, not the second one. C as in Charlie's chi-square test. Put your cursor, align with cursor with C and hit enter. So chi-square test observed is A, expected is B. Okay, you don't have to do anything. You go to calculate and hit enter. Again, we are looking for a test statistic, which is 22.529. And look at the p-value. And there is 1.28. First of all, probability cannot be greater than 1. So there is something wrong. The wrong thing is E minus 5 at the end of probability P. Minus 5 means the first number 1 is at the 5th place after the decimal. So that means p-value is actually 0.0000. First 4 are zeros and then 1, 2. So it's a very small number. It's almost equal to 0. So p-value is less than 0.05. Reject the null hypothesis. If we reject the null hypothesis, then at alpha equal to 0.05, we can conclude that age group and brand name are dependent. Okay. So that's it. I will stop here today. If you have any question or comment, please write me a note. I'll get back to you as soon as possible. If you like this video, please share with your friends. And please subscribe to my channel by hitting the red subscribe button at the bottom right corner. See you next time. Take care. Have a nice day.